Hello, welcome back. We are finishing up section 1.2 today, the graph of a function. We have accomplished the following learning objectives in the previous video. We looked at the rectangular coordinate system. We graphed one or maybe more functions. We studied intersections of graphs, the vertical line test, and intercepts. So now what's left to us is sketching and using graphs of quadratic functions in applications. So we will jump ahead to relevant slide. So our example is about maximizing profit. So Milton's Automotive Parts buys copper spark plugs for Audi sports cars from the manufacturer. So he gets them at $3 each, and then the company has $11 in labor that's associated with selling these. So that's not, the $11 has nothing to do with how many get sold. That seems to be kind of a fixed cost for them. Daily demand is found to be 15 minus x. So this is in dollars, and then x is the input when they sell x plugs. Okay, so that's the setup. Our task is to find sales level at which maximum profit occurs. So if you want to picture this in sort of a metaphor, profit is a long ways away from us. Right now, all we have is a description of how much it costs him to purchase these things, and then how much he can sell them for as a function of how many he wants to get out the door. Okay, so we need profit, and in particular where profit is largest. And then as a follow-up to that, we're going to get a graph of this profit function. Okay, so first task first. We don't even have a profit function, so that's probably a great place to start. If you recall from section 1.1, profit is, or maybe from your econ class, profit is the difference of revenue and cost. So there's a place to begin. Can we get revenue? Can we get cost? Well, revenue we can get if we know that we sell X items. And according to that demand function we were given earlier, we can charge 15 minus X dollars per spark plug if we want to get X of them out of the shop. So if we multiply those two things together, X times 15 is 15X, X times X is X squared. There's our revenue function right there. Okay, and then for costs, we've got a similar situation. We know that we can, that he's got, Milton, I guess, has $11 worth of daily labor associated with the plugs. Presumably there's other labor going into other stuff. So this is a fixed cost no matter how many of the plugs get sold. And remember, that's our only input here. X is the only thing that gets to vary in this case. So, and X is only keeping track of how many spark plugs are purchased and sold. So, purchased from the manufacturer and then sold to customers. So he gets them for $3 each. And that means that this is the variable cost associated with his operation. So variable cost is $3 times the number of parts that he acquires, and then $11 for labor. And then if we do some of the combining like terms, we're still going to get a negative x squared here. That doesn't combine with anything else. We do have a couple of x terms. We've got a 15x and a minus 3x. That's going to give us 12x in the middle. And then we got to be a little bit careful with the sign, but still manageable. We'd have subtracting 11, so it's actually minus 11 here. So this is our cost as a function of how many plugs get produced, get sold to customers. So the shape of this is called a parabola. We can actually, this could be in bold if we really wanted to. This is the definition. The parabola is the shape of a function that looks like this. So a, b, and c are all constants. It's got an x squared, maybe an x, maybe a constant. And most important to us, since what we're really looking for is maximum profit, the thing that we're after is where is this thing biggest? And the great thing about a parabola is it has a very predictable formula for how we get a maximum out of it. So the vertex is found, at least the x-coordinate, the input value at which the vertex occurs, is found by this formula. So b is the linear term of our quadratic function, a is the quadratic piece, the coefficient on the quadratic term. So if we take a ratio of these nice constants, it's going to tell us where the input value at the vertex. If you're one of those curious folks who actually wants to know where this comes from, in just a couple of weeks when we get into actual calculus for this class, we're going to be talking about how to find maximum values of any function. And in fact, what's going to fall in our laps, courtesy of calculus, is this very formula if what we're working with has a form of a quadratic function like this fellow right here. Okay, so what the upshot is, maximum profit's going to occur at negative b over 2a. Well, okay, so b in our case, this linear term is 12. And then a, the term in front of x squared, the coefficient on x squared, is negative 1. Of course, the 1 is kind of imaginary there. We don't need to write it, it's assumed. So we've got negative 1 times 2 in the bottom. Don't forget the negative out in front, otherwise we'd have a negative x value, which doesn't really make sense in the context of this problem. Selling negative spark plugs is kind of weird. So what we've got is negative 12 over negative 2, which is 6. And then, stating that in words, MAP, Milton's Auto Parts, makes maximum profit when selling 6 spark plugs every day. There was a part B to this, so we're supposed to sketch a graph of profit. And again, we're using graphing calculators in this course, so I don't have a whole lot of reticence in recommending that as a resource. Wolfram Alpha is also a great place, and that's where some of the graphs in these PowerPoint slides have been generated. But just to point out, we could figure out these intercepts on our own. Those generally help with graphing. Finding x-intercepts and y-intercepts, those are great ways to help get a feel for the picture involved. X-intercepts are found, these ones in particular, 1 and 11, are found when we set this output equal to 0. So if we let the y value, that is the output of the function, be 0, and then we solve 0 equals all of this stuff, then what we'll get by factoring is values of 1 and 11. You could also ask Wolfram Alpha to solve that for you, I suppose, but doesn't that take all the fun out of it? So the maximum, at least the location of the maximum is x equals 6. That's what we figured out with that negative b over 2a magic in the previous slide. And with a little help, we've got a graph. So we know that it has this parabolic kind of shape. It touches at 11 and 1 for its x-intercepts. Its y-intercept is arguably the easiest facet of this. If we go back to its formula quickly, here's our profit function again, and the y value is right there. If x was 0, then none of these x terms would be in the picture, and all we'd have left is negative 11. There's our y-intercept. That ought to be reinforced in the graph we've got here. So down here at negative 11, yep, looks pretty convincing. There's where our y-intercept is. So that does it for section 1.2 and graphing quadratics. We'll be back shortly for section 1.3. Thank you.